Okay, so I'd like to welcome Jon. He's giving a talk today on nilpotence and duality in the complete cohomology of a module.
Thank you, Scott. I'd like to thank the organizers for this. If anybody has trouble hearing me, say on the net or anything, let me know, please. So I'm going to talk about some work that I did this past year. Let's see, how do we do this? Here we go. Nope, that's not going to work.
Try clicking on the screen once.
There we go. Okay, so it's a sequel to a rather old paper that Dave Benson and I wrote some almost 30 years ago on products in negative cohomology. And in fact, you know, this is sort of one of our most cited papers for various reasons. But as I say, this paper was written back like 30 years ago. What I wanted to do was to sort of generalize this from the cohomology ring of a group to the cohomology ring of a module, finitely generated module over the group. The paper, by the way, I think is actually available on the web through the website. I submitted this in about the 1st of July, and 2 weeks later got a report back, and fortunately the referee liked everything except some notation in my horrible typing. So after correcting a myriad of little mistakes, it has been accepted and will appear in a journal called Contributions to Algebra and Geometry. It's a Springer journal. Here are the ground rules for what we're doing. We're going to work over a field of characteristic P. I want G to be a finite group. I want P to divide the order of G, because otherwise everything that I say is completely uninteresting. Every KG module that I'm going to talk about in this talk is finitely generated, so I don't think there's any question there. So finite dimensional modules. And for M a KG module, there is this dual M star, which is the Ham from M to K, and it is also a KG module with the group acting using the usual Hopf algebra structure. And we also have, because KG is a Hopf algebra, we have a tensor product, and it's made into a KG module by the diagonal map. In other words, G times M tensor n is GM tensor Gn. So this is for G in the group and M and N in modules cap M and capital N. Okay. Need a little bit of notation here. If we let M be a KG module and take the projective cover of M, capital P, then I want omega of M to be its kernel. Okay. And so inductively, what we could define what something called omega n to the nth power. That is where we just repeat this n times. So omega is to the nth power is omega of omega to the n minus first power of n. This for all n greater than 1. And the point is that we can do this in the opposite direction. We'll take omega inverse to be the co-kernel of an injective hull. Take M into Q an injective hull. And again, you can repeat this so that you can iterate this process so that I can define omega minus n. And I can define an omega 0, and that's basically just the non-projective part of the module M in the same way. And the thing to remember here, so one of the things that makes all this make sense, is that the group algebra KG is what they call a self-injective ring, so that projective modules are injective and vice versa. injective modules are projective. And so when I take an injective resolution, they're all projective modules in that injective resolution. And we also have sort of a calculus of these objects. That is to say, if I take omega m of omega n of m, that should be probably isomorphic to omega n plus m, and so on. If you do the tensor product, these things work out quite well. This last relation down here follows because of the fact that whenever I tensor with a projective module, I get a projective module. So that if I tensor a projective resolution of m with n, I get a projective resolution of m tensor n, and so forth. Okay, now let me just introduce the stable category. I'm not going to do a whole lot with it, but on the other hand, this is where sort of everything takes place. The objects in the stable category, again, are finitely generated KG modules. This is my category ST mod KG. The morphisms are usual homomorphisms from M to N, but you're going to factor out all those that factor through a projective module. So this has the effect, by the way, of making projective modules isomorphic to zero modules, the zero module in the stable category, because after all, the identity homomorphism would factor through a projective module and therefore be zero if the module itself is projective. And what we should say about this, I think Dan talked a lot about this kind of thing last week, is this is a tensor triangulated category. The triangles basically correspond to exact sequences, short exact sequences. But one of the important things here is that the shift functor in this triangulated category is in fact this functor omega inverse, omega minus 1. Omega and omega minus 1 are not really functors on the module category, but on the stable category they are functors in this particular case. Okay, so what we want to know here is how do you get cohomology products? Okay, and I want to go through this with you because this is really the important part of this.
Can I interrupt and ask one sort of, so why does one consider the state, what's the one sentence reason one considers a stable category? Because like I've been, like in the stuff I've got a lot, we deal with K theory where you're not really throwing out projective modules, which is the same as throwing out vector bundles. And so,
right.
So it makes me think that maybe we should be doing this stuff.
You get a lot of extra structure for the stable category, and it's it just the fact that it's triangulated actually gives you some gives you some extra structure that is helpful. And in a lot of the things that you want to do to talk about, say, classifying modules to the extent possible, it works better in the stable category than it does in the module category. You really just want to throw away the projective modules. When you take the tensor product, for example, you really don't care about projective summands when you get that for a lot of what we do. So the stable category is actually very useful in this regard. And things like cohomology actually take place in the stable category, although we define them using projective resolution. The maps are really in the stable category. Okay, so generally, if I wanted to find X from M to N for any ring R, what do? The standard thing is you take a projective resolution of the module M, and then you take the the homology of this cochain complex, which is halm of R into from the projective resolution of M into N. So this is sort of a standard construction, you know, that you would read about in any book on homological algebra. But let's just see how this works out, because this is how we're going to define the cup products. Okay, so the top row in this diagram here is a projective resolution of the module L. Well, it's an augmented projective resolution because I've got the module L in there. And the middle row is a projective resolution for the module M. And the bottom row is a projective resolution for the module N. Now, if I've got a cocycle from P sub M into the module capital M, this actually lifts to a chain map. That is because of the fact that the upper sequence is projective and the lower sequence is exact. By definition, I can get this omega 0 just by definition of projective module. I can get this a map of phi sub 0 from PM into Q0. And then this just propagates along and you get a chain map on this projective resolution. You can do the same thing if I've got a cocycle psi from Qn into N. I can get this propagates to give you a chain map on the projective resolutions from the Q resolution to the R resolution. So these, as I say, these two cocycles lift to chain maps. And this lifting is not unique, but it is unique up to homotopy. Up to homotopy of the maps. And the homotopy classes determine the cohomology elements. Okay, so one of the points of this is that the product that you get, which would be given by PM plus N to Qn to N, that can be taken actually to be the homotopy class of the composition of the two chain maps. So I've got a chain map from the P to the Q and from the Q to the R. And I take that composition and I get the homotopy class of that is actually the corresponds to the product of the two cohomology elements. Okay, now if I go back a minute and I look here, and instead of taking the resolution all the way, I just sort of cut it off and replace this by its image in the next map, and this one by its image in the next map. Then what I get is I get this next diagram where the end one is just omega n plus m of L, and this one is omega n of m, and then I've got my map psi. And this map, this phi here, determines this map again, sort of, it determines it uniquely in the stable category. Okay, it's not unique in the module category, but in the stable category, it's unique. It's going to be it's determined up to something that factors through a projective. Okay. And so the fact is that we can actually write xn of mn as really the halm from omega n of m into n. In other words, this map will actually represent that cohomology class quite well in the stable category again. And then on the map from the projective resolution P into M. This is the cohomology from ML. Okay, I can do translate this, and this in other words, this halm kg of omega m of L to M in the stable category is the same as isomorphic to, in a very natural way, to the translation of these by shifting by degree n here. And so actually we can define the homotopic, the cohomology product as the composition of these two, which is what we're doing here. I'm just taking the composition of these two. Okay. So we get this composition, and that defines, as I say, this cohomology product. Now, what I've written here is the same as what I had before. But here's what you're supposed to notice at this point. You should notice that this doesn't depend upon N or M. It doesn't depend upon the degree. I can define I can define this shift. I can shift one way, I can shift the other way because I'm in a self-injective ring. And I can define a composition like this that would define a cohomology product. And this is in fact what we want. This gives us the product in all degrees on complete cohomology or take cohomology, and we'll talk about what that is in a minute. Okay. Okay. Now there's another way of doing this, and that is by doing what we call complete resolutions. Okay. A complete resolution. Here's a definition. A complete resolution of a module M is an exact complex of projective modules. So it's the image of a boundary zero here is in fact isomorphic to the module M, or is the module M is probably the way you want to say it. So what that means is that the resolution P2 to P1 to P0, that's a projective resolution of M. And going the other way, we're still doing projective modules. It's still exact. These are also injective. So going the other way, going P-1 to P-2 to P-3, that's really an injective resolution. So the positive part is a projective resolution of M. The negative part is an injective resolution of M. The modules are all, of course, both projective and injective. So I'll give you two examples of this just quickly. First one is just a cyclic group of order P. All right, now, so this is the cyclic group of order P is generated by a single element, call it little g, with g to the p equal to the identity. Now, if I do a little bit of a shift here, that is, change this around a little bit, let me let capital X equal to g minus 1. And the thing about capital X is, if I take it to the pth power, well, remember you're in a field of characteristic P, so the binomial coefficients, pth power binomial coefficients all vanish, except at the ends. So if I take X and I raise it to the pth power, I get g to the pth power minus 1 to the pth power. But g to the pth power is 1, so that's 1 minus 1, so that's 0. So in other words, x to the pth power is 0. And I can write the group algebra, Kg, as this truncated polynomial ring. It's a polynomial ring in X, and I'm going to divide out the pth power of X. Okay? So then I write down a complete resolution. I just need maps. Every one of these terms in the complete resolution is just isomorphic to Kg. That's a free module. Okay. If I take the map Kg onto the trivial module K, then what's the kernel of that? Well, it's going to be generated by this element X. And consequently, I can get a map onto that kernel by just multiplying by X. And now if I multiply by X, what's the kernel of that? Well, I claim it's going to be X to the P minus 1. And so it goes on like this. And so what you get is you get this long resolution where the maps, the boundary maps, alternate between multiplication by X and multiplication by X to the P minus 1. All right. So, so this is what the complete resolution is. It's just this long sequence, infinite in both directions, with the maps, all the terms being kg, and all the maps being either x or x to the p minus 1. And I'll point out something here. This is a situation which we call periodic, because it repeats after periodic terms, you know. And if you think of chain maps on this, it's easy to see that you can shift 2 in either direction and get the same thing. In other words, if I start, instead of starting here with P0, I started here with P0, it would still be exactly the same resolution. It would look exactly the same. So in this particular case, I can shift back and forth, and the complete cohomology, which I'm going to talk about in a minute, has elements in degrees 2 and -2, whose composition is the identity. But let's go on. Okay, so what happens when you're not in a cyclic situation? So I want to look at a group of order 4. Okay, elementary abelian group of order 4. It's going to be isomorphic to Z mod 2 squared twice times itself. And it's generated by G1 and G2. Again, I can say, okay, we'll let X be G1 minus 1 and let Y be G2 minus 1. And what you should notice is that X squared is 0 and Y squared is 0, because now I'm in characteristic 2, right? So here's what a complete resolution looks like. What I've got on the right, on the left-hand side here is a projective resolution of K. What I've got on the right-hand side is an injective resolution of K. The way you're supposed to read this, by the way, this is the degree 0. In degree 1, I have 2 copies of Kg. There's supposed to be a direct sum sign in there, but I couldn't figure out how to get a XY pick to put that in. So at any rate, so it's the sum of 2 copies of Kg. In degree 2, I've got 3 copies of Kg. And you guessed it, in degree 3, I would have 4 copies of Kg. Just its direct sum of those. And the maps are as given. The map from here to here is just multiplication by X. The map from here to here is multiplication by Y. So now when I do the injective resolution, I just turn all this stuff around. It's basically the dual resolution, and we splice it in. In degree -1, by the way, I get the same thing as in degree 0. In degree -2, I get the same thing as the dual of what I get in degree 1. So this is the situation that you've got. And what you should note is that this gets bigger as you go to the left, and it gets bigger as you go to the right. But in the middle, it's kind of small. Now, what this means, by the way, we're going to talk about what I'm going to say in a minute, or we'll try to convince you of in a minute, is that what we want to do to define cohomology products is define it as compositions of chain maps. Now, but if I have a chain map that goes negative degrees, or if no, let's put it this way. If I have a chain map that goes positive degrees, it's going to take something that's a direct sum of several copies of Kg here, and maybe map it into something that's only 1 copy of Kg. And what that's going to tell you is that you've got to have a large kernel there. Okay. Because I'm going from a large dimensional module to a small dimensional module. Okay, so at any rate, whenever I've got a homomorphism psi mapping omega n of m to n, I can lift it to chain maps. Okay, on the left-hand side here, here's my psi from omega n of m to n. I lift it to a chain map. from the projective resolution of M to a projective resolution of N, or a projective resolution of omega N of M. On the same time, if I've got an injective resolution of N, I can lift it from this injective resolution of omega N of M to an injective resolution of N. And when I do that, then I take these and I splice them together. And what I really have is a chain map of the complete resolutions, okay? So this is the way I'm going to define my cohomology product. The product of two cohomology elements is the homotopy class of the composition of their chain maps on complete resolutions, okay? And this works in both positive and negative degrees, because I can have on complete resolutions, I can have chain maps that work for positive degrees and chain maps that work for negative degrees. Now, let me just say real quick, when Dave Benson and I did this years ago, we did it a little bit differently, because if you want to just talk about projective resolutions or just talk about injective resolutions, the negative cohomology doesn't give you a chain map. It gives you something that's almost a chain map, except in 1 or 2 degrees. Okay, and that sort of is a problem. But you can define, you can do what the analysts do. I thought of it as I used to listen to a lot of measure theory talks where people talked about do something except on a set of measures 0. Well, okay, so do that. We'll define almost chain maps. Chain map except in a few degrees here. And almost chain homotopy except in a few degrees. And you can in fact define negative cohomology and the products using that notion. Okay. All right. Okay, now here's what we know. This is old stuff. Okay. If you look at the cohomology ring of M, this is a non-negative degrees, finitely generated module M. It's a finitely generated algebra. It's finitely generated over its center. It is also finitely generated as a module over the cohomology ring H star GK of just the trivial module. It's a PI algebra, meaning a polynomial identity algebra. It satisfies a polynomial identity, and you can do a lot with this. A polynomial identity might be something like xy minus yx. If it satisfies that, meaning all those are 0 for every element in the algebra, then the algebra is, well, commutative, right? Okay, and 2 by 2 matrices satisfy another polynomial identity, etc. So it is a PI algebra like that. It is not, however, graded commutative. It has irreducible modules that are more than just one-dimensional. Okay. The complete cohomology, where you throw in negative cohomology, this is not finitely generated unless the module is periodic. And in the case of the trivial module, so that you're looking at the cohomology, the complete cohomology of the trivial module, what Dave Benson and I proved, well, let me say this. What we know is that this negative cohomology is a nilpotent algebra. Okay. Actually, Dave and I did not actually state that in our paper, although we proved it certainly in some cases, and you can get it from that paper. Okay, so here we go. I want to define 2 ideals for you in this complete cohomology ring. First one is, well, let me give you some notation first, okay? So the cohomology ring of the trivial coefficients, positive, non-negative degrees, this I'm going to call H sub G star. The cohomology ring, again, non-negative degrees, and I'm putting a plus sign down here to indicate that, is just going to be E plus. And the thing with the hat on it, this is our standard notation for Tate cohomology. This is going to be the complete cohomology. Okay. And here's my first ideal. My first ideal is I'm going to take the K subspace. Okay, so for any n, I'm going to take the K subspace of this complete cohomology generated by the set of all elements M, with the property that if I multiply it by this cohomology ring in non-negative degrees, it has finite dimension. Okay, so the stuff that gives you finite dimension, all right, generates a finite dimensional module as a module over the cohomology ring of the cohomology ring of the module itself, the non-negative cohomology. And so I'm going to take all of those. This is a nice graded ideal. And while you have to prove that it's an ideal, but it's easy to see that it's an ideal. It's a submodule over E star plus. It's easy to see that easy to see that it's a right ideal. There's a little bit of a trick to showing that it's a left ideal, but it is a two-sided ideal.
So, John, one question here. So it's saying that if you look at the negative stuff, it all has finite dimension. Oh, I'm sorry. I'm sorry.
Okay.
Sorry. Never mind. I just retract my question.
All right. Okay. Okay. All right. Now we can define this a little bit differently. That is to say, instead of looking at it as module generated by the cohomology ring of M, let's just look at it as a submodule generated by over the cohomology of G, cohomology ring of G. Again, that has finite dimension. Okay, where that thing is finite dimension. And what you can prove is that these two are the same. And this is a sort of an important point. The reason why these two are the same, basically, well, it's easy to see that one is contained in the other. It's easy to see that the I tilde is contained in the I. Going the other way, you have to use the fact that the cohomology ring of M, this thing up here, is finitely generated over the cohomology ring of just the trivial module. Okay, so that's the first ideal. There's a second ideal. Now, if I just use the cohomology ring of the trivial module, that's this H star GK, that is a graded commutative ring. And so using that, I can call upon notions from commutative algebra. In particular, the notion that I want is Kroll dimension. And so what I'm going to do this time is I'm going to take the set of all elements M with the property that H star G modulo the annihilator of M has Kroll dimension at most 1. Now, Kroll dimension at most 1 means that basically it's sort of like a module over a polynomial ring in one variable. Okay, and what that means is that for any I, as the dimensions grow, it's a equivalent condition that that there's a bound on the dimensions of Hi of G times the element M. Okay. So in other words, as you multiply by higher degree things, there's a bound on the dimension in each degree. All right. Okay. And again, you sum these up. And the fact that we put Kroll dimension at most 1, by the way, means that the ideal I that I defined just a minute ago is contained in this ideal J. Okay. So as I say, you can make this equivalence with by bound of this Kroll dimension idea with a bound on the degrees of the elements. So if you let Jn tilde, I can do the same thing with instead of just doing this for the cohomology ring of the trivial module, I could do it for the cohomology ring of the module itself, for this E star plus. But there I have to just say it in terms of this bound rather than in terms of Kroll dimension, because this E star plus is not a commutative ring. Okay, so it's not difficult to see that this I star is contained in J star. We just said that. And the J star is a two-sided ideal. Again, you prove that. Okay. So we do get some bounds on this. For example, these come from the fact that we're dealing with finitely generated stuff, at least in positive degrees or in degrees above any number that you like. So if the gist of this is that there's a number B sub I such that In is greater than or equal to 0. And you can, in fact, say approximately what that is. So you can give a bound on that. The reason is that this In is stuff that is whose dimension, such that the dimension of the cohomology ring times the element is finite dimensional. Now, in positive degrees, this is going to be a finitely generated ideal. And consequently, if every one of the generators has finite dimension, then the whole thing's going to have finite dimension if there are only finitely many generators. And so what you get is that there's an upper bound on all of the generators that you can get in this particular case. And so we get this notion that the In is 0 for n sufficiently large. Okay. All right. Now, suppose I let A and N sub B be the annihilator of, take the set of all J mod I in H star G, and you look at H star G modulo the annihilator this is the annihilator for the J algebra, or the part of the J ideal in degrees above some number B. Okay, and this has to have Kroll dimension 1 because of a finite generation again. And so what we get from this is that we could choose an element zeta in the cohomology ring of the trivial module here, such that this thing is a finitely generated module over the polynomial ring generated by zeta. And in other words, what we want is zeta, if you're familiar with this, we want zeta to be a one-element homogeneous system of parameters for this thing modulo the annihilator. Okay, and so if we take U as the ideal generated by annihilator B and zeta for any power of zeta, then this is going to be finite dimensional. This H star G mod U is finite dimensional. And what you get out of that is that for this element zeta, for any n greater than or equal to B, this element zeta, this map, in going from multiplying by zeta, is going to be an injective map. So this is an important point, and we're just getting this from a little bit of what we know about we know about the commutative algebra here. Okay, and so here's the picture. So we'll get a couple things out of this. Probably one thing you get out of this is the reason why I went into mathematics rather than art. I mean, you know, it's sort of crude here, but here's the idea. The complete cohomology is the stuff between the two big black lines. Okay, and the degree 0 is right here. It actually centers around degree -1/2, although that's not really a degree. And then you've got this ideal I, and you've got this ideal J. And the ideal I runs out from here, somewhere, you know, in positive degrees. In negative degrees, the ideal J eventually becomes the whole thing. Okay, if you go far enough in negative degrees. So this is the story, that this is what it looks like. Okay. Now let me see. Let me see what we could get out of this. Okay, in order to get further with this, in order to get the statements about nilpotence that I want, we're going to need Tate duality. So this is classical Tate duality. I'm not clear exactly how Tate originally defined this, but it's been generalized several times. And the way it works out for us is that it's a non-degenerate pairing of xn with x of -n-1. So the sum of the degrees is -1. Okay, and it is a non-degenerate pairing. That takes some proof, of course, but there is such a thing. And here's how you define it. So first of all, we should note that if I take xmm, that's the same as x of m star tensor m. M star is the k dual, and m star tensor m is Hom k of mm. Now Hom k of mm is a ring, just as xmm is. Well, the multiplication that you get on xmm can be, in fact, you know, given through this ring in some ways. And so but at any rate, the way Tate duality is defined is this. You take this is my x upper n, this is my x hat upper -n-1. N can be either positive or negative here, by the way, but the degrees of -1. What do? You take these two, you do a composition. I think I can just show you this. No, let me not. You just do a cup product, but I'm dealing with xmm, so I can actually do a composition. I can multiply the two. And so I get an element in h-1 of Hom k mm. And now I want to map that into h-1 of gk. And how do I do that? Well, this is what? This is the ring of m by m. Whatever the dimension of m is, it's the dimension of m times dimension of n matrices over k. It's k homomorphisms. And consequently, all I do is I just take the trace map. So this last one is just given by the trace map. Now, the important point about this is that this thing is just sort of composition. It is a cohomology product, and the cohomology product is associative. So what you get is this. The upshot of this is that if I've got alpha, beta, gamma, and these are three homogeneous elements, I want the degrees to sum to -1. So that means that if gamma has degree n, then alpha beta is going to have degree -n-1. And the fact that this cohomology product is associative means that if I take gamma times alpha beta, this is my duality, this is my pairing up here. If I pair gamma with alpha beta, I get the same thing as if I paired gamma alpha with beta. In other words, this is just an associative statement that I can take that alpha across and do gamma with alpha first and then with beta. And it's all because this is because this take cohomology is given by this product. Now that gives you a very nice little result, which we use quite well. And that is if you've got a homogeneous element in this cohomology ring, a negative degree, and if there exists another element of negative degree, such that the product is not zero, well, that's going to happen if and only if there exists an element in positive degree, such that gamma alpha is positive degree, well, it might be zero, but gamma alpha is not zero and has positive degree. In other words, if I can take two elements that in negative degree whose product is zero, then I can find an element in positive degree, which multiplied times one of them gives me an element in positive degree. In other words, it's going to cross this line. It's going to cross the zero line. And the reason is very easy. If I've got alpha, beta not zero, and these are both elements in negative degrees, I take the Tate dual of that element. So that's what gamma is. Gamma is the Tate dual of that element. And so gamma of alpha beta is not going to be not zero. I would usually take it to be one, but that's fine. Just want it to be not zero. But I've got this associativity. I can take this across. But the point is that the degree of gamma is the degree of alpha is -1 minus the degree of alpha minus the degree of beta. So so that gamma alpha is going to have positive degree here. Okay. So as I say, if I've got two elements in negative degree with non-zero product, then I've got to take an element of positive degree and multiply it times either one of them and get it into positive degree. Now this does some funny things to us. I'm not going to have time to go into the bound of this, but what you get out of this is if we've got this, we said before we had this bound such that this ideal I in degree n was zero if n is greater than this bi. And what's going to happen the other way is if we've got this alpha and ion with n less than minus bi minus 1, then beta alpha is going to be zero for every element beta in I. So, and the reason is because I otherwise I would have to have this element in positive degree that multiplied times alpha gave me something in positive degree that was non-zero, but it would be too big a degree, is what it amounts to. Okay, and finally what we get from this is that this ideal I is nilpotent. Okay, now why is that? Well, see what we've got here is if we've got elements that are negative degree elements, if I've got two elements in I, and if I multiply them together and get something that's not zero, on the one hand, the sum of the degrees has to be smaller than this B, this bound B. On the other hand, the sum of this, each one has to have a degree that is greater than minus B. So everything's bound. So if I take a long string of elements in I, any substring is going to have degree that's bounded above and bounded below. Consequently, if you start looking at the substring strings starting at zero, they're going to have to be a lot of repeats. It can't get too big, it can't get too small. That means I've got to have a lot of them that actually have degree zero. The products have degree zero. but that then is an element in XMM. And then in XMM, it's got to be in the radical, and the radical is nilpotent. So that's basically the way this proof goes, is you bound it above and you bound it below if products are non-zero. Okay. Now, I could do something similar with J. I'm going to go through this fairly quickly. And I can prove that J star is a nilpotent algebra. This is by taking the negative cohomology in J, and I prove that that's a nilpotent algebra. And so, and the way you do that is that you can always multiply this element zeta and get something. If I've got something that's non-zero, I can multiply it by the element zeta and get something in positive degrees. And then, so finally, what we're going to get here, and this is sort of the main theorem of the paper, really, is if I've got any finitely generated indecomposable KG module, it's not periodic or projective, then the negative part of its cohomology, complete cohomology, is nilpotent. It's a nilpotent algebra. And the way you get that is, well, J is basically all of the negative part of the cohomology except for a little bit. And that little bit, if you multiply too many elements from that little bit, you're going to get something that's eventually in J. So as I say, this was the main thing I wanted to get out of this was that even for the cohomology ring of the complete cohomology ring of a finitely generated module, indecomposable module, the negative cohomology part is a nilpotent algebra. I'll just mention you can get something that I call the nilpotent streak, periodic streak, I'm sorry, which is what you do is you take this part of J that can be generated in arbitrarily large negative degrees. And that is going to be actually periodic. The element zeta that we talked about would give it a periodicity. And so this is a nilpotent two-sided ideal. I did give an example. I'll just show you this. So this is an example, a diagram of a module. The vertices in the diagram are basis elements. So it is a 7-dimensional module. There are 7 basis elements there. The arrows tell you what happens when I multiply by x, y, or z. X, y, and z are, this is over a elementary abelian group of order 8, so p is equal to 2. And the point is that that for this particular module, I do get this ideal J to be non-trivial. And the trick is that the module is set up so that there is this on the right-hand side, that parallelogram is actually a periodic, not submodule, but quotient module. And so you play off this periodic quotient module to get that this ideal J is not equal to the ideal I. I get something non-trivial. So I think that's about all I'm going to say another time. So thank you.
Questions for John?
Yeah, I have a question. So, so when you take x to MF,
Yes.
and so let's say you take the negative to the part. So, do you like say when the topics of homology elements are equal to 0?
You mean?
For the trivial module, we know.
For the trivial module, we know the answer in many cases. Yeah.
Okay.
It's I mean you sort of have. I mean, I'm not sure what you're looking for. You sort of have to look at the elements carefully. It's hard to say exactly what happens. But this difference between the I and the J are sort of thin. And so in the I, basically, well, I guess you can have, I think you have to have non-zero products for the I.
Other questions?
No.
Let's thank the speaker again.